Alright guys, story time. Let's see, a long time ago in this country there were three experiments that you have to know, you should know for chemistry, well, chemistry's sake. It kind of blurs the boundary between chemistry and physics, but the first one's J.J. Thompson. I forget what the J and the J stand for, but Mr. Thompson, it's always called the Thompson Experiment or the Cathode Ray Tube. Let's see, it's also called the Crooks Tube Experiment, but in other words, Thompson didn't discover or invent the tube, the machine, but he'd certainly used it to explain what he thought was happening with the atoms and such. So what, and this is like a, I'm sure he posed for this picture, it's all fancy and stuff, and this is, I think this might be the tube that he used, I'm not sure. Well, it's about 1897 or so, our first bit of evidence that atoms are made of smaller things. It's called a cathode ray tube, probably because this thing, this plate, this metal plate over here was hooked up to a high voltage battery, and it served as what we call the cathode. This over here served as the anode. What then ended up happening was the cathode would spit out these little particles represented by this orange arrow here, and they would travel through to the anode. There's a hole in the anode, though many of them would get right through. These particles would. And then the particles are traveled between these two charged plates. One plate was negative, one plate was positive. It just so happened that the ray, the beam of particles, was pushed away from the negative plate and toward the positive plate. Well, let's see, electrical charge, what's the conclusion? This beam of unknown particles must be positive or negative. Let's see, if it's attracted to the positive and repelled from the negative, oh yeah, this screen over here was painted with some kind of paint that glows when struck by radiation or particles. Here's another cartoon of the same thing. I'll show you this in lecture if you've never seen it, or you can Google it or YouTube it. High voltage power supply provides the negative cathode and the positive anode electrical potential difference. The cathode spits out the negative electrons. They travel for a small space before they hit the, in this one it's some kind of blockage with a hole in it, and those electrons travel through pretty much straight until they encounter the electrical field. It also works with a magnet. I think Thompson actually used a magnet and an electrical field to help him narrow down the details on this electron thing. Here's a more accurate, here's a picture of the one I have. It's not my picture, but it's one just like I have. And the magnet deflects the magnet and or the electrical field of the positive negative plates. They both deflect the moving electrons. If you take physics semester 2, you'll talk about the interconnectedness of electricity and magnetism and how electrical particles are affected by, moving electrical particles are affected by electrically charged particles are affected by a magnetic or electric field. Interesting. So then he very carefully measured the strength of the charge on the plates. He measured the velocity the electrons were. Oh, well, at the time he didn't know they were electrons, but he quickly kind of figured it out. I don't know if he coined the word electron or what the deal is, but anyway, electricity, electrons, electrostatic forces. He probably didn't coin that. I don't know, I have to look it up. He measured the velocity of the particles, he measured the charge on the plates, he measured the displacement that the particles experienced from the center line to the place where they hit the screen. And from all that he was able to figure out, remember this now, he was able to figure out the charge to mass ratio by equating the force on those particles to the strength of the electric field. He wasn't quite able to measure the charge on the electron, he wasn't quite able to measure the mass of the electron, but he was able to measure the charge to mass ratio. I believe it was Maxwell's equations and such that helped him. Oh, and also, who was that dude that measured the physicist? I forget that first wrote down the equation for electrostatic forces. Anyways, and he concluded the electrons were negatively charged. He might have coined that, although I don't know. Probably Volta or Galvani coined the negative phrase. So remember that. But he did make one big mistake. Thompson did. He thought, therefore, an atom that was giving off these electrons looked like some kind of plum pudding. Guess they ate a lot of plum pudding back in the day, where you have just kind of a uniform atom, uniformly positively charged throughout, and these little teeny blue seeds. In this picture, it's blue, of negative electrons. Here's one where the positive charge of the atom is kind of showed as purple, evenly distributed across the whole thing, and little negative electrons. And through his cathode ray, he was able to pull those electrons off of the atom, send them flying off into space, deflect them with the electric and magnetic field, and watch them glow. Oh, did you know that this cathode ray tube is the great-great-great-great-grandfather of the modern, no, not the modern, the old-fashioned television set, where those old TVs that had a really heavy, large back on them, that was basically an electron gun shooting electrons at the screen up front. A lot of static electricity generated from that. I don't know if your parents or your grandparents had one of those TVs. Maybe you ever tried to lift one. They're heavy. I don't even think they sell them anymore. I have to go to Best Buy to check it out. Second experiment, Rutherford, Ernest Rutherford. Oop, too far. Sorry, come on, don't do that. Second experiment, Ernest Rutherford, just a short time after that, maybe 10 or so years, 12 or so years, he and some of his assistants, that's young, that's old, notice still he has the stash, so he and some of his assistants fired bullets at a thin, super thin piece of gold, and watched and measured to see what would happen to those bullets as they encountered the gold foil, the gold atoms. Well, most of them went straight on through, passed through the gold foil like it wasn't even there. But every now and then, one of those particles would be deflected to the right or to the left, either a little bit or a lot, and he was scratching his head like, what in the world is going on here? How come most of them get right through the gold, but a few of them get scattered to the side, deflected, or even backward? He didn't know it at the time, but these alpha particles themselves are positive nuclei of the helium, of a helium atom. They had just sort of recently discovered radioactivity, and a guy named Geiger was working for him. He had kind of invented the Geiger counter. In any case, here's Rutherford's conclusion. His model was that as he shot these alpha particles, and he knew what they were called, but he didn't, again, know they were he didn't know they were helium nuclei, written like this. They have 2 positive protons and 2 neutrons. He didn't know that. He did know that it was positive. He shot them shot a whole bunch of them coming from the left to the right through the gold. These are the gold atoms here and here and here. Gold is amazingly malleable. It can be hammered into a very, very thin sheet. And so those alpha particles mostly just went right on through. Sometimes if they came close to the nucleus, they would be deflected a little bit. And sometimes if they accidentally came head-on to the nucleus, they would be ricocheted backward. So he didn't actually have proof that the nucleus was positively charged, but he did assume that. He knew the alpha particles were charged positive. He assumed the nucleus was also positively charged and very, very dense. In other words, almost unmovable. And indeed, the protons and neutrons in the nucleus are very, very dense. And he also said that most of the atom is empty space, which is hard to believe. I still can't wrap my head around that fact that atoms are mostly emptiness. They sure seem solid. That's because the electromagnetic strength of attraction between the electrons and the protons. They seem so solid because you really can't, overcome that electromagnetic, electrostatic attraction. Yeah. All right. So remember that conclusion as well. Last experiment was this guy. He's famous. Robert Millikan, an American physicist, I believe. That's young. Brace yourselves, man. He looks old. He looks a little bit ornery here. Man, he's not too happy about something. But anyway, I like this picture. So retro. This was about the same time as Rutherford. Millikan did his famous experiments. If you look into it, it's actually kind of some shoddy science. It wasn't very well done. I mean, he's a genius, and it worked, sort of, but if you look at the details of his research and his data, it kind of sucks. It's pretty poor, pretty poor, what should I say? He gathered a whole bunch of data and he only looked at the data he wanted to look at. He ignored the rest of it, which is bad science. But he's famous. It worked out. I actually did this experiment at the University of Iowa as an undergraduate student in physics. You spray some oil droplets into this chamber, and those oil droplets drop down into a hole in the middle of a plate. Sometimes he had ionizing energy that would make those oil droplets have 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9, sometimes 10 too many or too few electrons. That would give the oil droplets a negative electrical charge. And he put a negative charge on this plate down below and a positive charge on the plate above. By adjusting the amount of negative charge on the plate below and the positive charge on the plate above, let's see, if this plate is negative and these oil droplets have extra negatives, that means they repel, and so he could make these oil droplets kind of suspend in midair without falling any further. And he looked through the viewing microscope over here, his eye was over here, and he measured the voltage that he would have to put on this plate down here to make these droplets stop falling. And he kind of tabulated that. And after looking at thousands and thousands and thousands of bits of data, like I said, some of them pretty crummy data, but he was pretty prejudiced in his selection of data. He was able to prove that he could, by looking at the integer incremental amounts of charge on each droplet as compared to other droplets, he was able to, brace yourself, he was able to get the charge, the electrical charge on one single electron. I'm sure he won the Nobel Prize for this. Very famous. And because of that, since he now had the charge, he could easily use Thompson's data with the charge to mass ratio to basically, what would it be, multiply charge to mass. So if you took the reciprocal of the charge to mass ratio from Thompson and multiplied it by the charge on the electron, that will give him the mass of the electron. Whoa. So Millikan, in a sense, got a handle on the mass of the electron, but definitely came up with a good measurement on the charge on the electron. All these three experiments crucial for proof that atoms are actually made of smaller things like nuclei, like electrons with charges and masses. Hey, thanks for watching, guys.